Okay, now let us start with another very important uh, method of producing alcohol from alkenes. This is the second method. We call this as hydroboration oxidation. Hydroboration as you can see that the method involves two steps. The first step being hydroboration, the second step being oxidation. Let us understand how first of all the reaction occurs. Remember, if you take an unsymmetrical alkene, right, and if you subject it to hydroboration oxidation, the first step is to react it with pH3. pH3 is diborane, so first thing you react it with pH3 and the solvent, which is called tetrahydrofuran. This is the solvent, and in second step you perform its oxidation. Now oxidation generally is done with H2O2 in presence of a hydroxide. All these would result into a product. The net product, if you properly observe, is actually a product which is obtained by adding water onto this part here. Water is added here. Now if you properly understand where H plus and OH minus get added, you find that hydrogen gets added onto the carbon having less hydrogen and OH gets added onto the carbon having more hydrogens. This is exactly opposite to your Markovnikov addition. So when you perform Markovnikov addition, the product generally, the major product generally is a 2-propanol. This is here 1-propanol, which is a major product. So what are the highlights of these reactions? 1, addition of water according to anti-Markovnikov. Addition of water according to anti-Markovnikov addition. So anti-Markovnikov is like the reverse of Markovnikov. Second, no rearrangements. So there are no rearrangements, which also indicate that there would be no carbocation intermediate. And third, you have no, or let's say the addition is syn, which means H and OH, they add from the same side. For example, if you have an alkene like this, and if you subject it to hydroboration oxidation, I'm just writing HPO, no need of writing both the steps. I have to know that my product will have OH and H added from the same side. So this is H and H. Here normally H and OH are added on the same side, so this is syn addition, right? So basically this I can put it like this, and I may write down here syn attack or syn addition. So now after having understood what this is, let us go into the mechanism of this process, of how exactly and why exactly there is no rearrangement, or why is the addition syn, etc., etc. So the next thing that we explore is the mechanism of hydroboration oxidation. Now let us talk about first of all understand what BH3 is. BH3, boron hydride, is a molecule in which boron is sp2 hybridized, and boron doesn't have its octet completed, and it has this empty orbital left with it. So we have this empty orbital with boron. This is the empty 2p orbital of boron. Now, having not got its octet completed, and thus by having this one empty orbital, right, the molecule BH3 behaves as a Lewis acid. So octet not completed, and therefore BH3 behaves like a Lewis acid. BH3 behaves like a Lewis acid. Now let us understand what would happen when you have your BH3 been added along with alkene, right? So if I take an alkene like this, the same alkene, CH double bond CH2, and if I put boron here, just remember, if I try adding this two, the first thing that happens is, and there's this empty orbital, right? So the first thing that happens is this moves here and this moves here. Before we get the actual product, there is a cyclic transition state attained. Look at this, CH, CH2, BH2, H. Sorry, I have to put only in which there is more negative charge here, there is positive charge here. See, this is the transition state, right? Let me call it as TS. Now you need to understand this, that why would boron, get electrons from the pi bond and get attached with this carbon? Because when boron gets attached with this carbon, there is positive charge generated on the carbon here. Now you know that this carbon can accommodate positive charge better because it has this methyl group, and due to its plus I effect, positive charge is more stabilized here on this carbon. On the other hand, if I have boron shifting onto this side, right, and getting connected with this carbon here, you may find that if boron gets attached here, there is positive charge on this carbon then, but this is a primary carbon, and the positive charge on this carbon is not as stable as when you put it here, and therefore the positive charge resides on this carbon only because it is more stabilized by the presence of methyl group attached to it, right, the plus I effect. So we have this transition state generated, and eventually after this transition state we may find that the further reaction would convert this into a stable intermediate or a stable first step product. So let us put it like that. So we have our transition state here, and this transition state eventually gets converted into the final product, which looks like this. Right? This is an alkyl borane. Now the steps get repeated to see there are two more hydrogens left here, and because of that a similar reaction can occur two more times. So I may write repeat 2 more times. So every time one alkene now gets added, right? So I'm just putting 2 times CH3 CH double bond CH2, right? So we're repeating 2 times, and finally we end up in getting a trialkyl borane, CH2 CH2, and this is 3 times, and this is boron. This is called a trialkyl borane. This trialkyl borane now is subjected to oxidation. So this is the first step, and this trialkyl borane now is subjected to oxidation. Oxidation is done using H2O2 and OH minus. Now let us understand how oxidation occurs. You know that boron is now a kind of, right, and when you subject this to a combination of H2O2 plus OH minus, OH would abstract a proton and you end up in getting OOH minus plus water. Now this OOH minus which is formed, right, it enters into the empty orbital, 2p orbital of boron, because now again trialkyl borane is, you know, electron deficient, as octet of boron is not completed. So now let us understand how the further reaction occurs. So now I am going to show you how OOH, oxyhydroxide ion, which is generated from hydrogen peroxide, how would it add onto this trialkyl borane. So let us now start with the first step. Boron acts as a Lewis acid here, and it doesn't have its octet completed. So the next thing that you see is this, and you have O, O and H. Now this is negative. Now the point is, this bond here is a very weak bond. Oxygen-oxygen bond is very weak, and hence there is this small rearrangement taking place, and you can see that the electrons of this bond would shift here onto this oxygen, and this alkyl part would shift here. And so finally what happens? Finally you have boron, and now you have oxygen, and then minus H2O, or minus OH, minus OH minus. Clear? Now once again, this is supposed to be repeated how many times? Repeat 2 times. If you do that, you end up, just a moment, I can just make this a little. If you do that, you get a final product which looks like this: P O O. Okay, this is called trialkoxyborane. This is called trialkoxyborane. This trialkoxyborane again is, the boron still has only 3 bonds, so this can add here, and you have O, this again becomes minus, And now what happens is this would move out. So as soon as this comes in, this moves out, and we find B OH plus O minus. Now if I repeat this, so if I this is the first alkoxide ion which I get. Now if I repeat this 3 times or 2 more times, you end up in getting H boron, O, O and O, H, H and H, which is nothing but H3BO3, and 3 times CH3 CH2 CH2O minus, sorry, O minus. So these are 3 alkoxide molecules, alkoxide ions, and these alkoxide ions would further take protons from water. So H plus received from aqueous medium, and this would give us 3 molecules of CH3 CH2 CH2OH. Okay, so this is how we get the final product. As you can see that in alkoxide, the oxygen, hydrogen generally comes from BH3. So when I if you closely look at this structure, or if you closely observe the first process, the hydrogen that alcohol receives is actually the hydrogen coming out from boron. So hydrogen gets added here, so it comes out from boron, and the OH that comes on to boron, and then that OOH finally the oxygen now combines with alkyl chain to form alkoxy chain. This O actually comes from hydrogen peroxide, and H comes from water. So basically this H is derived from, or let us put it here on this side, this H is derived from BH3. Remember this? And the OH that CH2 receives, that OH, oxygen comes from hydrogen peroxide, and H comes from medium or water. So overall, if I have to put it here into that actual thing, this H from medium or from water, and this H here from BH3. So you need to remember, so one H comes from BH3, the other H comes from water. Oxygen obviously from, this is the one which comes from, peroxide. This is the one which comes from peroxide. So I think this is what we have for hydroboration and oxidation. Okay, the next reaction that produces alcohols from alkenes is called oxymercuration, demercuration. Again, the reaction involves two steps. The first step is called oxymercuration, the other one is called demercuration, which is nothing but reduction using sodium borohydride. Now, the general form of this reaction can be given like this: a C double bond C, when treated with mercuric acetate. Mercuric acetate is like OAC and OAC. You know, OAC minus is equal to CH3COO minus. And now you find that there is this first step taking place, and you have C single bond C, Hg OAC. There is a positive charge generated here, right? And so now from the valence shell of mercury, electrons are given onto this carbon, and this results into formation of a cyclic transition state or cyclic intermediate, right? And that would be nothing but this now becomes partially positive, right? And this becomes partially positive, and this is partially negative. Now here you can see that the electrons of pi bond generate this cyclic intermediate. Now the question is, where would the positive charge be? Why is positive charge on this carbon more settled? Depending on the structure, if you have more substituted part here where there are more alkyl groups, then positive charge remains here. Why? Because the positive charge remains on that carbon which is more substituted, and hence if alkyl substituents are more, it gets more stabilized, and therefore one carbon becomes partially positive, the other part becomes partially negative, and you find that this is the transition part. The next step would be like water reacting onto it, or water getting added onto this, and you have C. And when this happens, you find that electrons now shift properly, and you have OH, H plus, and you have HgOAC. Now there is this deprotonation, and we find that there is this carbon with OH, C, and HgOAC. Now if you take sodium borohydride in step number 2 in alkaline conditions, it can very easily reduce this part here and replace it with hydride or hydrogen then. So we end up in getting OH, C, and H. So this is the basic way in which oxymercuration, demercuration occurs. We would take up an unsymmetrical alkene to understand this reaction more more precisely, and try to figure out whether the addition is Markovnikov or anti-Markovnikov. So let us take up an alkene which is not symmetrical. It's an unsymmetrical alkene. The first step with HgOAC twice would result into formation of CH3, CH3, CH. See, this is like CH3, and then you have the mercuric acetate added, so CH2 and HgOAC. Okay, let us put this as a weak bond here. right? This remains partially positive, this remains partially negative. Now you find that the positive charge remains on this carbon, and that's because it is more substituted. It has more substitution here. So having more substitution, the positive inductive effect would effectively stabilize this positive charge on the carbon, and hence this carbon remains partially positive. So when the water molecule now does the nucleophilic attack, you find that this moves here, and you end up in getting CH3, CH, CH2, HGOAC, and you have now there is this deprotonation, which results into CH3, CHOH, CH2, and HGOAC. The next step is reduction with sodium borohydride, generally in alkaline condition, so OH minus, and now you have the final product, which is CH3, CH, OH, CH2, and H. So here you can see that the water gets added here. Final, if you consider what exactly happens, it is addition of water only, but OH is derived from water, which is the medium here, and H is derived from NaBH4. Overall, it is Markovnikov addition. As you can see that hydrogen gets added onto the carbon having more hydrogen, so Markovnikov addition, that's the highlight. Second, NT addition, right? NT addition. And the third most important thing, no rearrangements. Whenever a reaction proceeds through a cyclic intermediate, right, there are no carbocations generated as such, and therefore we find that there are no intermediates. There is no carbocation intermediates generated, and therefore there would be no rearrangement. So whenever a reaction proceeds through cyclic intermediates, you may not have any rearrangements taking place. So we've done 3 different methods of producing alcohols from alkenes: the normal acidic hydration, 2, it is the hydroboration oxidation, and 3, it is the oxymercuration demercuration. Now what I would now do is I would give you an alkene, and we would try to add water by all these 3 different reactions and try to figure out what products do we get. So let us take up the new alkene and let us perform all these 3 reactions on that same alkene. So as I was talking about comparing the 3 different reactions of alkenes producing alcohols, let us understand what products do we get. For example, in this first reaction, where we use water under acidic condition for adding onto an alkene, the first step would be protonation, and you may find that the first step would be CH3, 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 CH, and CH3. A secondary carbocation. This is according to the Markovnikov addition, where H plus adds on to CH2 to generate a secondary carbocation. If H plus would have added on to carbon here, we would have got a primary carbocation, but secondary is more stable, so we generally get this. However, now there is a possibility of shifting this positive charge onto this adjacent carbon, and by doing so we can generate a tertiary carbocation. How is this done? Simple. We call this as methyl shift. So what we do is 1, 2, methyl shift. And what happens because of that? We get CH3, C, CH3 plus CH, CH3 and CH3. So this is rearrangement done. After that, there is this addition of water, which is like this, and you have CH3, C, CH3, OH, H plus CH, CH3 and CH3. And this finally, upon deprotonation, would give you CH3C, OH, CH3, CH, CH3 and CH3. This is the final product. This is the major product. So I may just put this properly. And we have our final product, which is here. This is our major product. Let us try doing the same with HPO. Here there will be no rearrangement, so it is just plain and simple anti-Markovnikov addition of water. You just have to remember that whenever you have HPO, it is anti-Markovnikov addition of water. So you have CH2, CH2 and OH. There would be no rearrangements. There is no rearrangement observed in HPO or oxymercuration, demercuration. And the final product here would be a simple CH3, CH3, CH3. Here there would be no rearrangement, but it would be a kind of Markovnikov addition. So while oxymercuration and demercuration generally follows Markovnikov addition, HBO follows anti-Markovnikov addition. However, in both these cases there would be no rearrangements observed. So if you go through these products one by one, you find that there's one here. So this is major here. You can very easily understand that all these three different products, right, they are formed from the same alkene but using different types of hydration reactions. Okay, let us take up the second method of preparation. Here we use carbonyl compounds and we perform the reduction of these carbonyl compounds. This would give us corresponding alcohols. Now first of all, let us understand what kind of carbonyl compounds we're talking about. Carbonyl compounds can be aldehydes or ketones, or we could take up carboxylic acids, or we could probably take up esters. These are some of the important carbonyl compounds which are used for making alcohols by reduction. Any compound which has this group in it, right, this is a carbonyl group, and a compound having this group in it would be called a carbonyl compound. So now let us first of all understand the reduction of aldehydes and ketones. So aldehydes or ketones. Aldehydes and ketones, they can be reduced by different reducing systems. One, we can perform catalytic hydrogenation. Now catalytic hydrogenation would be hydrogenation in presence of PT, PD or Ni generally. Another way of getting alcohols out of aldehydes and ketones is by performing reduction using nascent hydrogen. And nascent hydrogen can be obtained from, one of the ways of getting it is sodium plus ethanol. And the third method is by reduction with metal hydrides like lithium aluminium hydride or sodium borohydride. So there are three basic ways of producing alcohols from aldehydes and ketones, and these are the three important methods by which you can perform the reduction. I would first of all give you the general reaction, and then I would also give you a small mechanism regarding the reduction. So let us now first of all take up the general equations. The general reactions include taking aldehyde and reacting it with any one of the three systems, H2 and Ni to lithium aluminium hydride or sodium borohydride, sodium plus ethanol. Any one of these methods could be used, right? And it would generally give us R, C, H, OH and H. Here one hydrogen gets added here and one hydrogen gets added on oxygen. The pi bond breaks and there are two hydrogens added. So these are the two hydrogen atoms which are added and the pi bond is broken. This is a primary alcohol. So you can see that here aldehyde, any aldehyde here, we may put it as an aldehyde, gives a primary alcohol. If you take up a ketone in the same way and perform a similar reaction, then you end up in getting a secondary alcohol. So this is a primary alcohol and this here is a secondary alcohol. So these are the general reactions by which reduction of aldehydes and ketones could be done. I may even, as I've told you, I may even give you some information about the mechanism. Let us understand that. So if I take up any simple reaction like this, and if I use lithium aluminium hydride, for example, lithium aluminium hydride can be written like this. It is basically aluminium hydride when treated with lithium hydride. It gives you H minus forms a complex. So basically it is a complex compound in which hydrogen here forms a coordinate covalent bond with aluminium. This hydrogen generates a coordinate covalent bond with aluminium, and so what happens is you have hydrogen going here. So you have R, CH, R dash, O minus, right? And this O minus then connects with aluminium to neutralize and form AlH3 minus and Li plus. You can repeat this. You can repeat this about three times, and you end up in getting R, CH, O, R dash, and this entire thing I'm sorry. And this would finally undergo hydrolysis in acidic condition to give you R, and then there would be bond breaking taking place here. So there would be R, CH, OH and R dash. How many of them? 4. Plus aluminium hydroxide and lithium. You need not write more about it. So this is your final product, right? So this is a simple mechanism by which you get your alcohol. I have taken a ketone here. I could have as well taken an aldehyde here by putting H here, and the same thing, the same mechanism I would have given, and instead of getting a secondary alcohol, in case of aldehyde I would have got a primary alcohol. So this is the mechanistic part. Now let us take up the other carbonyl compounds and figure out how the reduction of these carbonyl compounds occur. So next is reduction of carboxylic acids. In general, there are two systems which are used for reducing carboxylic acids, one of them being lithium aluminium hydride. Remember, sodium borohydride cannot be used. Lithium aluminium hydride, and the second is B2H6 diborane. Diborane is more specific in reducing carboxylic acid, and here we write cannot reduce other functional groups like nitro, halo, esters, etc. easily. So B2H6 is more specific, and what would be the reaction? As simple as that. Any carboxylic acid taken like this, if you have to reduce it, just remember, if I take lithium aluminium hydride, it would first of all reduce, you will have one H added here and one H on oxygen, and then you have R, CH, OH and OH, isn't it? This would lose water because there are two OH groups on the same carbon, so minus H2O, and it gives you R, CH, double bond O. Furthermore, one more lithium aluminium hydride reduction and you get R, CH2, OH. Overall, you find that there is this, there's this part getting broken, this bond getting broken. One hydrogen here forms water, which is separated here, and this part becomes RC double bond O and H, which further gets reduced to RCH2OH. Clear? So basically a primary alcohol is formed here, right? This is how carboxylic acids are reduced, right? You may take up one more example for reduction of carboxylic acid. For example, if you take up RCOOH, and if you reduce it using lithium aluminium hydride, you end up in getting this here is benzoic acid, and this would produce benzyl alcohol, right? So this is about reduction of carboxylic acids. Now we would take up reduction of esters. Reduction of esters. Reduction of esters can be carried out in three different ways. One, using lithium aluminium hydride. Two, using a system of sodium along with ethanol like what we have for aldehydes and ketones. And the third method which is used here is catalytic hydrogenation. Catalytic hydrogenation is basically hydrogenation using CuO and CuCr2O4. This is generally the catalyst which is used, and we can have catalytic hydrogenation which can reduce esters. In general, if you have an ester, the reduction with, let's say, lithium and aluminum hydride would first of all break this bond, and let's say if I put lithium aluminum hydride, I'm going to get RC double bond O. I'm just showing you the disconnections. R dash OH. Both of these parts would get one hydrogen each. This remains as it is. There is no further reduction, but because aldehyde formed has a carbonyl group, it gets further reduced. So further, aldehyde gets RC double bond O and H gets further reduced to RCH2OH with lithium aluminum hydride, or any of the other systems that we have here. So what would be the summary of this entire thing? The summary of this entire thing is the bond breaks here. This part becomes one of the alcohols, this part becomes another alcohol. So two different molecules of alcohol would be separated in case if these two alkyl groups are different. If you have same alkyl groups, right, then if this, you may have, normally you will have different types of alcohols formed, but because there is one R and one C, and if this R dash also has same number of carbons as this part here, then it would generate the same alcohol. So most of the times the alcohols, they can be different, but you may also have same alcohols formed. Let us check this out with different esters. Let us reduce them and figure out whether the alcohols formed are same or different. Let us perform the reduction of all of this one by one. So this part here would produce two types of alcohols, CH3, CH2OH. It has two carbons, and this part would also give you CH3, CH2OH. Here both the alcohols would be same. Once again the bond breaks here. Let us find out what products do we get. CH3, CH2OH, an alcohol with two carbons, and here it will be CH3OH. Let us break this one here. You get CH3OH, and here you get CH2OH. So we get two different types of alcohols in the two esters taken here, but we get the same type of alcohol produced here in case of this the first one. So you have to know the alkyl groups, and then you will or the hydrocarbon groups, and then decide whether the same alcohols would get formed or you get different alcohols, right? Okay, let us take up some very specific examples and try to understand the reducing power of different reducing agents. For example, the first case here, there is an aldehyde group here, and it can be easily reduced by both catalytic hydrogenation as well as lithium aluminum hydride. But there is a pi bond here, and a carbon-carbon double bond is not affected by lithium aluminum hydride. So the product here in case of lithium aluminum hydride would be the reduction happens only at the aldehydic group, and this would be the product. Whereas here, because H2 and PT or a nickel, they are capable of reducing carbon-carbon double bond as well. So carbon-carbon double bond is reduced and this is converted into CH2OH. So here you understand the selectivity that lithium aluminum hydride or sodium borohydride, they are ineffective on carbon-carbon double bonds. Lithium aluminum hydride here in the second case can reduce aldehydic group, and it should be not effective on the carbon-carbon double bond. But when a carbon-carbon double bond is conjugated with a benzene ring, when it is conjugated with a aromatic ring, then it is reduced even by lithium aluminum hydride. So a special case, when you have a carbon-carbon double bond conjugated with aromatic ring, it would get reduced even with lithium aluminum hydride. Okay, sodium borohydride. Sodium borohydride, this is a special molecule here with a ketonic group and a carboxylic acid group. Sodium borohydride cannot reduce carboxylic acids, or it will not be effective on esters or anhydrides, right? It is able to reduce only three important structures. One is the aldehydic structure, a ketonic structure, or an acid chloride. So this can reduce aldehydes, ketones, or acid chlorides. But carboxylic acids are not reduced, and therefore here the final product would be COOH remains as it is, and this gets converted into an alcohol. On the other hand, lithium aluminum hydride can reduce all of them, right? Acid chlorides, acids, esters, they all get reduced with lithium aluminum hydride. So this is OH and this becomes CH2OH. So this is a little bit about the selectivity which you should remember. I have taken some very specific examples to show you the selectivity of different reducing agents, right? So we've completed the reduction of carbonyl compounds using different reducing agents. Now we would quickly move on to the third method of preparing alcohols, and that is from Grignard reagents. So let us do that synthetic method, right, of producing alcohols from Grignard reagents.